Hello, everyone. My name is Bahram Asiabanpour from Texas State University. And it's my pleasure to talk to you about additive manufacturing and the things I have done the last 20 years. And I want to talk about different aspects of research, education, and service you can do in additive manufacturing. In recent years, it's been very big talk about that in media and everywhere, but there are some facts that I want to share with you about how to do the research, education, and service in this field. And I would be happy at the end to answer any question you have through this webinar or after through email. Feel free to email me or call me if you need. I'm going to leave my information at the very last slide. So I'm going to start from very beginning, from the definition part and different aspects of additive manufacturing, just in case somebody is not familiar with the whole process and what are the latest technology. Then specifically, I'm going to talk about the research I've been involved in the last 20 years through developing a new additive manufacturing system, as well as collaborative activities we did under research activity using different types of additive manufacturing, and how to teach additive manufacturing and how utilize that for outreach and service work. And then I'm going to close with what's the pros and cons as of now and what's the future looks like in this field. Basically, additive manufacturing, based on the new definition, and used to be called 3D printing or rapid prototyping or variety of names, freeform fabrications, is a process of joining materials and making objects layer by layer. Sometimes is point by point, sometimes it's going to be linear depositions. So it's a variety of ways you can build, usually from bottom up. Also, we have seen more and more processes that so you have additive and subtractive added, and there are a variety of ways that you can build it. So this is very general definition of the additive manufacturing. Process is different from process to process because we have dozens of different additive manufacturing, some commercialized, some still under development, but usually all of them, they follow 8 key elements during the whole process, from the idea all the way to the functional part. So I want to go briefly through those elements as well. So it starts with the CAD file. CAD file can be generated using a solid model software. Variety of software can make that file. So it's very common practice these days. And you generate file in a certain format that is next step. But another way to do that is going to be reverse engineering, that basically usually by some other tools like laser scanning or other type of software and hardware, you can capture the data and utilize that for additive manufacturing as well. And I have a case study about that I worked with some other researchers on that as well. So after you have your CAD file, through reverse engineering or drawing that, you are going to convert it to STL. As of now, STL is a de facto file standard that is triangular shape data, but that you can make any geometry, and is limited to only geometry. But more and more efforts are being done to add other features like color, texture, material, accuracy, standards, units to that as well. So because it's much needed and it needs to be moving with the latest technologies. As of now, it still is the very beginning file that was used for the first SLA process. It still is being used. After that, you transfer data to the machine. So in this, as of now, is a human role. Something is very important. What's the orientations and how do you want to build it up? As well as also sometimes unit is very important. Sometimes your CAD data versus your software or 3D printer is not matching. So you have to make sure they are using the same unit. It's not inch versus millimeter. So that's going to be very important, so you don't make too big or too small types of parts as well. Then I think okay, the next step is going to be machine setup. Very limited options usually have using 3D printers, but some of them, they give you options for making faster or better quality or denser. If there is the case, you are going to use it during the before printing step. Then the build process is happening. Depends on the processes. You may add glue binder, or you use energy to bond the particles together to make the final part. Then there is material removal from the build chamber. That depends on what we are using. It could be very simple or could be lots of work involved into that. Then you have the cleanup and post-processing, that usually you have to add glue or reinforcement and sandblasting to basically make it looks professional and usable at this stage. Then is ready for application. So application could be variety of things, could be very simple, just form. Basically we call it 3 Fs. One is form, fit, and functions. Form is just for evaluating how does it look like. For some products that's going to be enough. Fit is making sure that this product, this part is fitting the bigger assembly. And finally, function, which is basically one functionality to be used right away after out of the machine. There are a variety of technologies that we can group all machines under one of those. One is going to be binder jet, basically like the Z Corp or 3D Systems powder-based printers, that basically you print binder and color to make the part. It's very fragile at the beginning, and then you need to add reinforcement to that. So it's starting from the powder and then making it layer by layer. Second group is going to be directed energy depositions. That energy could come through laser, electron beam, plasma, or similar type of technologies. And basically you melt, sinter the particles and bond them together. Third group is material extrusion. Basically, often it's going to be plastic, but sometimes you can use ceramics or other materials. You extrude that and build the part through the extrusion. This is one of the most mature one as of now, because it has been studied enough and has been tested enough with variety of processes. Then we have material jetting. Basically, you, instead of bonding them through glue or binder, basically you print the small droplets of wax, photopolymer, or those type of materials on the previous layer and bond them together. We have powder bed fusion, basically is a source of energy, and then masking selected area. Then we have sheet lamination. Basically, you have a solid sheet that you can bond it to the previous layer and then cut through the laser. And finally, you have a liquid, the start point as a resin, and then photosensitive liquid is going to be solidified through shining the laser. So all these processes basically can make parts with variety of qualities and cost. So I want to talk about the specific process that I was involved in development from the scratch, from the idea part all the way to final product that we were able to make. So that was called selective inhibition of sintering. So the idea was to make parts quickly in a very low cost way. So as I listed here, any new ideas to make it to the final part, you need variety of things. You need the machine. The machine itself has mechanical hardware, control system. Then you have your software part. How do you generate pad generation? What type of material you use and how to optimize that. So all are the challenges that are involved. And usually it leads to patent products and publications. So this process is specific. I'm going to start from picture A. Basically, you spread the powder, plastic powder, and then you print liquid in the selected area. And then a heater comes down and sinter solidifies the whole layer. Since it's plastic, it's gonna melt and bond the entire layer to the previous layer. And you repeat that for several hundred layers. At the end, you will see something like a block in part C that you can move to another liquid to separate that selected area. In this specific case, we use salt solutions. So when we are done, you put it in water, salt is dissolving, so you can take out the parts out of the surrounding material. So it was very quick and very low-cost way to make near functioning parts. So this specific one has lots of development and research directions that we followed. One part that I was heavily involved was about developing the algorithm and flowchart for the software, because your start point is going to be a CAD file, a steel file. Obviously, this is not usable. There is no software that can answer all types of additive manufacturing needs. So we have to customize our own toolpath. But this is one of about 10 flowcharts. So it was very extensive software development to come up with basically this final toolpath. So as you can see, toolpath in this specific case was, if you want to make, for example, this bearing, you need to print in selected area in green and then hatching in the red area. You have to repeat that layer by layer. So it has a slicing, defining loops, defining also hatch. So and you repeat that for all layers. So sometimes for several minutes, taking time to make that form. And so that was one aspect of that. Heavily, you have to customize your toolpath through coding. So it needs its own research, how to make it very efficient way that can work for variety of CAD with variety of geometries. So that was one aspect that I was involved in that. Another aspect was about the material. So in this specific case, we knew that we are going to use powder and we knew we are going to use liquid, but which one was very, very vague. So we studied more than maybe 100 different liquids and more than 10 different commercially available plastic powders to come up with the one that has best properties that we needed, which was the flatness, strength, and good separations. So it was heavily experimental. This should be something you can print, and it should result into something that you can have a clean cut at the end. So it's not easy because there is no previous studies or anything in this area. So you have to do lots of experiments and then justify that. What happened, to the material science or physics and impact agglomeration. So variety of fields coming together just to study how this is happening. What is happening with droplets impact the powder? Then what is happening when the evaporation happening, and then how do you separate two layers from each other so that hard shape from surrounding can be separated quickly. So that was another aspect of that. Lots of material studies as well. Then it comes to optimization. So you have just one machine and you can make the parts, but how do you know it's optimized? Optimization means good strength, so it's going to be functionality of mechanical properties. It should be accuracy, so X, Y, Z size. It should be about the shifting problem that lots of additive manufacturing processes have. So how do you optimize that? It could be about the surface quality as well. So, and you have to consider all of them. Lots of them have trade-off or contradicting behaviors. So you need to consider them as an overall optimization. So it's lots of design of experiment and surface response RSM methods that to optimize all at the same time. So it's lots of aspects of research also could be in this direction that has been done. So overall, optimization was something that we develop, and you can see some of the sample parts after extensive research, and you can see the accuracy and the strength at the same time, which is, as I said, is not always coming the same direction. Sometimes they are contradictory. And we made a variety of parts on that. And when I look at that now, if I want to continue in this field, there are, based on the new developments, I see multi-material is another opportunity that we can change the material or multi-layer or make it composite material now is possible. You can make multiple head, it doesn't need to be just one. It could multi-axis systems. So it's not only build up in Z direction, you can make it in a variety of angles. So make it faster, make it more accurate. More and more you will see additive manufacturing and subtractive hybrid systems is coming. So you can add that to the system. And also more and more you can do optimization considering quality, time, and cost. Usually you have to compromise in one of these three because you cannot have all three at the same time. So it could be software, could be hardware, could be material studies, and any of those. So any of those processes has lots of area of expansion and improvement. So that's my experience from this development. And I want to talk about a few other things that I have done as a collaboration using additive manufacturing with other researchers. Like this one is a work with forensic anthropologists. Basically in that field, they are finding lots of skulls, lots of bones that they want to identify the person identity, how old it is. But building the face is going to be a very important part. Lots of times these skulls are in the hands of police and or law enforcement that they don't share it with them. So the only tool they have is going to be laser scanning and get the cat file out. So in that case, they did that. So they laser scanned the file and we did the rest of the work. We used a variety of software to improve the STL file, to improve the cat file, to convert it to STL file. So it was a few years ago, so the software and hardware was not enough for processing that much data. So it was different approaches we took until we were able to make it a thick, good surface quality to be able to print it. Then they did the rest of the work with adding tissue and thicknesses to identify the person. So that was one aspect, utilizing additive manufacturing and reverse engineering to collaborate with law enforcement for identifying a missing person. So that was very successful, and that was a case. They found a person, 23 years old, female with a broken head. So that was one case that was used additive manufacturing to be solved. Another collaboration I did was with companies. Companies have some ideas. For example, in this one, they tried to use centrifugal force for different applications like lifting mechanisms or windmill type of applications. So as you can see here, it has combination of simulation, dynamic simulation, data collections, parts and product design and development. So we did the whole thing, and as you can see, several parts was made using additive manufacturing processes, and that process was good enough to use it as a functional parts. So as you can see here, some parts was here as a plastic functional parts, some we use water jet, some we bought, some with mechanical components, and all things together led us to be able to test the concept and measure and evaluate the concept as well. So that's another aspect, using additive manufacturing for functional parts. And that's one way that it happens a lot of times, especially we are using that collaboration with industry. And then I use that additive manufacturing for a variety of senior design class for manufacturing engineering, as well as teaching that as a standalone course, specifically additive manufacturing. So I'm going to show you some of the projects that we did during the different years. For example, this one was just using loam machine that is almost out of business now, but we use that for the metal casting purposes. So a student experienced the whole process from beginning CAD to final metallic part. Another example was utilizing that for making a new product, for adding flashlight for drill. So that was something utilizing, again, additive manufacturing for making part of the components that you need. And you see through these examples that basically additive manufacturing is one of many processes can be used. And we never forced to use all components additive manufacturing. It should be always a smart selection. What cases you want to buy, what cases you want to make, what cases additive manufacturing is making sense. So it's always very important not to force it, push a button and have a product. That's not happening. So that's something in the media, it's a hype that you will see all the time. Another example of that we work with a company for outdoor light fixtures that, as you can see, again, mix of additive manufacturing and traditional manufacturing to finalize a product that with one hand, the person can replace the light. So that was a specific need for that customer. Another example, again, to customize certain product for batteries that we use additive manufacturing to test variety of ideas, and later on we made it industrial scale injection mold for that product. So that was additive manufacturing was used for test and evaluation as well. Then I want to talk a little bit about using additive manufacturing for service. We use that extensively for outreach from K-12, from the kindergarten all the way to 12th grade. It's been very, very helpful, very successful. I see some students after many years, they come to engineering program just because they were involved in some of the camps we had. Usually it's a week-long camp that we had, and we make it a mix of fun activities, like as you can see, going to a river and measure, for example, depth and flow and other things. And then we teach them about the CAD solid modeling, and then finite elements sometimes, and then show them additive manufacturing and make the bridge. So basically, it's a combination of art and engineering. So they make their own parts, their bridge, and then even they make it landscape. So it's a 1 week of fun, but they are heavily involved in lots of engineering aspects under this program. So it's been very successful, and year after year, we have it in a variety of ways. So sometimes it's focused on renewable energy, sometimes it's on the engineering steps, but it's been a very, very good tool and innovative way to engage students. So as I said, it's been very successful in recruitment. From very young age all the way to high school kids, it worked very well. And obviously, additive manufacturing has lots of benefits. We see more and more option, customization, easy to use, and lots of people can have it at home in their shops and quickly. With low cost of labor and manufacturing skills, you make your own part. So in that aspect, and even sometimes it's making possible to make parts that was not possible before. So in that aspect, it's been very successful tool for lots of applications. At the same time, there are some drawbacks. Some of them is basically media hype. Some of them is because they are not mature enough yet and it's under development. More work needs to be done. So obviously it's going to be affected short term for manufacturing, some skilled worker, but they can be trained in the new areas. As of now, most of the processes have limited materials. So that's the limitation to each process has limited materials. Easily you can copy the other people's idea and reproduce it. That's the drawback again. Sometimes people can abuse it and make dangerous things like guns, and the only thing you need is just designing and then printing that. So that's also some of the drawbacks for this. Obviously, pollution and also environmental effect is another thing to consider. Even with the current 3D printers, we had some issues about how to basically, where do we put the waste material, or sometimes the liquid that is generated by the process. And repair is one of the issues that some people, they ignore at the beginning. It's very difficult. Sometimes we have to wait months till somebody can come and fix very small problems we face with the machine. So the workforce for repairing is not available, and sometimes very expensive, consumable, and repair. So it's going to be very difficult in that aspect. And future, obviously, I want to finish on time. Obviously, more customizations is available, more material customization, especially live tissue and industrial scale metals is the promising areas coming soon. It goes smaller and smaller while we go bigger and bigger. So from the nano scale to full house construction can be 3D printed. And finally, if you can expand the idea of composite and material, you can have variety of products, very extensive choices, way beyond the limitations we have right now. And finally, 4D printing is one of the ideas coming, self-assembly and self-curing, those type of things that is another aspect that some people suggest that it's going to be more and more we will see in the future. Finally, I want to introduce also the journal I'm involved with some other colleagues. It's International Rapid Manufacturing, which is the media for publications. So if you are interested, if you have done some research and you want to publish, consider this journal as well. And if you have any question about any of these things, I would be happy to answer you. My email is below. It's ba13@txstate.edu. Or you can call me or find me any way possible. I would be happy to answer question if you have right now or in the future.